Hello everyone. Today we'll start with session 3 of week 3 and we will be discussing about services, config maps and Istio for K8s networking and configuration management for AI workloads. So from the Kubernetes services point of view, the various service types which are available, okay, we'll just be discussing everything in brief just to have the completion but not going into the details of everything here. So we have this cluster IP, node port, load balancer and headless type of services available in Kubernetes. So this cluster IP is basically for the internal purposes of the various applications which Kubernetes services provide to us. It's by default and it's basically a stable virtual IP which is inside the cluster only, and it is used for pod to pod communication. So there is a cluster thing which is there in Kubernetes service, and from pod to pod, if the communication has to happen, that has to basically be a part of a stable virtual IP, which is basically inside the cluster. Node port is generally used for development purposes. It exposes the service on each node's IP at a static port, okay, and that is basically used for dev bar debug purposes only. Load balancer is actually a production thing which is generally implemented when you implement your Kubernetes services on production environment, and we will have a hands-on of what actually these provisions of load balancing are used when you use AWS or any of these cloud services. A brief idea about how it actually does the load balancing. So we will see a preliminary hands-on on all of these basic things today, and in the next session. Okay, so this is basically used for production inference endpoints. The headless thing is actually a concept wherein we are talking of stateful things. There is no cluster IP here, and DNS returns the pod IPs directly. So basically, here that's a virtual IP. In this case, it is having specific IP addresses, right? So this is essential for stateful sets and distributed training, because in case of distributed training, if you have specific IP, it's very easy for you to actually connect to those distributed nodes or distributed pods or whatever you are talking about. Okay, so basically headless services are the backbone of distributed training, and this basically is a standard stable DNS entry point nowadays for the initialization, okay, for so many things. Okay, so gateway API is generally used nowadays instead of ingress. Now ingress is a standard protocol which is basically used for connecting, right, two points, and basically it is the way in which you have the two endpoints getting connected in case of networking. Okay, and we are specifically interested to understand from the ML team's perspective as to why this is very very important, right? So we have done some small programs which will tell you about how this routing layer, okay, is basically used for connecting, right, your app to the cluster operator or the gateway, right? So this is how basically we are trying to discuss this in brief. Now the basic idea why we are discussing all of this is lot of the AI workloads will have a specific type of some model, okay, which will basically be a training image type of thing, okay, which has certain code. You can use PyTorch, you can use any of these things, and then this is in a container, right? And then every person will have some configuration map of with what particular parameters you would like to actually train the model, right? It's not that everybody would require the same batch size, okay, or the same parameters. It can vary. And then the idea here is to isolate this particular image in the container and the configuration part of it, so that every time when you use this particular image with a specific type of a configuration, you need not again retrain it, right? So that is the type of isolation which you can get. And this is very very important for a lot of training jobs, right? So that is the reason why intentionally we are covering this specific thing, because it will be useful when you start using dockers for training lot of your workloads. And this is one of the things which people should start using, right? You should use configuration maps. We'll see how basically we can do it in a small program. Okay, so then pod starts a container, and in that container at present you have this configuration map with batch size 128. So the basic idea is, if you have to have different training runs, okay, with the same training image, you can actually have different configuration map values. That is the reason why we will discuss a bit of configuration maps as well today. Okay, so now this is how actually it happens. So as I told you, this is very very important to understand that if we are having the same training image, okay, and we want to train it with different configuration map values, okay, for different training runs, how are we going to do it? So for example, uh, here if you see this API version 1, and this is one type of a configuration map which is basically having hyperparameters for training, right? And this hyperparameters for training, I showed you batch size 128. It can be 264, it can be 355, whatever, okay? And then the learning rate is this, maximum steps is this, model architecture is llama 3 minus 8b. So tomorrow if you want to change the model architecture, you want to change the batch size, okay, you want to change certain specific configuration, okay, uh, and you have to basically use the same training image if you want, right, with certain other parameters to change, okay, you can easily do it without basically trying to again retrain your whole model, right? And that is where you generally create one more thing which you talk about. There is this training configuration, and then there is something which is called as secret, right? Secret basically is the weights and biases. So if you talk of latest things like federated learning, okay, so on and so forth, uh, if you are able to get the weights and biases of a specific model, you can actually backtrack and see what the data is, or what privacy concerns are there, so on and so forth. And then these hugging faces tokens, right? So one of the things which people use these secrets is that you actually need not, okay, send the information, okay, of your API keys or your HF tokens, okay, inside the Docker and send it to other persons. So the basic idea is to have this isolation of certain things which are very very secretive, which are very very unique, okay, instead of putting it into container and then basically trying to pin it into that, and uh, which needs to be shared to so many people. So this is one specific thing which we will try to do today. Of course, a very very brief emulation type of thing, but these are all things which are actually used in production environment nowadays. So this is actually a concept of service mesh for interference traffic, okay, interference traffic, inference traffic, sorry. So inference traffic basically means what effectively happens is there is this mutual TLS between all the pods, right? And then there is zero trust network inside the cluster, okay. And then what effectively happens is, when you are in a production environment, okay, there are two models. Let us say there is one model now, which is an inferencing model, and this model is running, okay, and now you have another model which you feel that it is actually a improved model, and you want to shift all the traffic of this particular model to this, right? You immediately don't actually transfer the whole traffic, okay, to the new model, but you basically have a canary inference rollout wherein you route 10% to the new model, 90% to the stable model, right? And basically gradually you do some things like load balancing, and then go on shifting, okay, your uh, inference rollout to make this into 100%, because you want to observe, right, as to what effect you are getting when you are shifting your inference rollouts to this new model, right, instead of this old model, to check, okay, so many things. So you don't shift all of them at once. So that is the reason why you basically do this type of service mesh type of inferencing traffic analysis, right? And then there is observability, and then rate limiting, okay. So how do you protect inferencing endpoints from unnecessary request bursts, so on and so forth. So here we are using a virtual service type of a stuff, wherein 10% can read to the new model version, whereas 40, 50, so on and so forth, and then gradually 100%, okay. So we'll see this. There is this LLM inferencing type of small demo program which we'll be using, okay. So this is what actually in brief about the service mesh type of inferencing traffic. Okay. One more thing is the storage class, which we should basically remember a bit, wherein we are talking of storages for AI workloads, and then there are these type of operations which are generally carried out: read write once, read write many, read only many, so on and so forth. So read write once basically is something like a single node read write, and the default is NVMe local SSDs. This is basically a faster approach, but not shareable across the pods. Okay, so read write many is multiple node read write simultaneously, required for shared dataset access during distributed training. And read only memory is multiple nodes read only file. This is efficient for shared model weights served to many inference pods, right? So storage class for AI clusters specifically, you have got managed NFS, you have got a local scratch space for data set staging, and then you have got high performance parallel file systems, right? So these are various types of storage requirements for AI workloads, which you should remember, right? So your Docker containers, okay, should allow all of this type of operations, okay, in the whole environment setup when you start using all of these, okay. So from the lab perspective, I'll just go on and tell you as to what we are going to cover. We will have the concept understanding of each of these labs, okay, and then maybe in the next session we will do hands-on in detail, or in this session we will do something and in the next session we will complete the hands-on, right? So this would be the approach. So now let us try to understand the config map or the training configuration part, okay. So the idea here is, we are trying to externalize the training hyperparameters from the image, right? From the image, in the sense it's the Docker image which we are talking about, okay. So here it is a config map. We are using some API, okay, and the reference is a certain specific section of the slide, okay. So don't worry too much about on that particular session thing, because certain sessions I have changed the slides and the content, but the only thing which we should understand is this config map thing which I just now told you. So this basically stores non-sensitive key value configurations. That basically means batch size, learning rate, maximum steps, model architecture outside the container image. Okay, so this means you are isolating both of the things. There is an image, okay, and then these are certain hyperparameters. So now tuning a hyperparameter basically now revolves around just editing the config map, and it will never be a rebuild of the total training image. Please understand, a lot of us, when we start doing things, when you change the hyperparameter, you again rebuild the whole model, right, which actually is not correct. So we will have to use this config map type of approach for tuning our hyperparameters and reduce the rebuild of the training image, and then it's consumed by the training pod through env forum config map reference. So values land directly in the containers environment. So this basically means once we are using these this config map thing, okay, the information which is being actually used, right, it directly goes to the container environment through the env from. Okay, so this is the manifest in brief. Okay, I showed you about this particular type of a manifest. Now, how actually it works? Now, there is this pod, and this is the training pod, and there is this config map, and this is the training configuration for this particular training. So, data is stored in plain key value pairs, as I told you previously also, and it is visible in clear text. So, never use a config map for secrets. So, see, it's a plain key value pair, so it should not be used as for secret things, right? And any pod in the namespace can reference the same config map by name. Changing a value updates the config map objects immediately. The running pod still needs to restart and then pick it up. So the basic idea is, once you change the value of a config map object, okay, this dynamically cannot be actually seen by the pod. So you have to actually restart the pod so that it takes that config map again. Okay, the new one actually. So for this, the commands which we generally use will be apply and check. So cube control apply the YML file and then config map training configuration. So one of the notes here is pair with a secret for anything sensitive. Okay, so this van db, hugging face tokens. Okay, so this is weights and biases actually, and hugging faces tokens or any tokens which you are supposed to be using, okay, never belong in the config map. So it has to be actually in the create secret script. Okay, so this has to be remembered. So now how is actually the training pod using this thing? Okay, so here when you are saying the training pod is supposed to use the config map information, the secret map information via env from, okay, and my pod is actually utilizing these two informations for training. Okay, so this basically means that a one shot training container that pulls its entire environment from two sources. That basically means there is this container which needs to be trained on, and it needs to pull the information about the entire environment from two sources, a config map and a secret information. So secret will contain the weights and the biases as well as the token information, and the config map will tell us about the various hyperparameters. So neither hyperparameters nor tokens are baked into the image. Very specifically, this is the discussion. Tuning a run or rotating a token never requires a rebuild. Okay, so this is one of the important things which we should understand. So restart policy, that means never this model is a method, or this approach is a method, a finite training job, not a long lived service. So restart policy is, if you go on restarting it, this is basically a issue. So this basically is a model which talks about finite training job, right? So this is the manifest, there is this image busy box, and then this is the trainer. So restart policy is never, it has got certain commands, we'll use all of that. Okay, and this is how that basically things happen. So config map train configuration fly, the secret ml tokens go to the pod. This is the training pod. So env from merges every key from both the sources straight into the containers environment. So no per key wiring needed. So that basically means the whole of the information goes straight into the container environment. Okay, and the secret ml tokens must exist first, created with create secret.sh before applying this pod. That basically means we are talking about the secret ml tokens which should be there before the pod actually applies every information. Okay, so check inside the running container kube control execute training pod. So this is basically grep and batch size, so on and so forth. So this basic thing tells us about running this in WSL. If you run it in PowerShell, then I will use a different command. So, but for the WSL thing, this is what is the command, right? So, so this is how it's going to happen. So run create secret.sh first. The ML token secret, this pod references must already exist, or the pod stays stuck in the create container config error. That basically means certain information needs to be there in the secret, otherwise it will just keep on checking for that, and pod will stay stuck. Okay, so now one of the things is the idea about config map, secrets, and then the training of the pod. Now we're talking of specifically the headless service, right? Headless service in the sense cluster IP none basically means stable per pod DNS instead of one virtual IP, right? So this basically means if it's a cluster IP, all the pods, okay, will have one virtual address. But now we are talking of a headless service. That basically means we will have stable per pod DNS instead of one virtual IP. So each of these workers, whichever we are trying to run, will have a specific IP address generated. So that basically means none means no virtual IP is allocated for this service at all. A DNS lookup on the service name returns every pod's IP directly, not a single load balanced address. So this is not something wherein the headless service we are talking about, right? So headless service basically means there is not just a single virtual address and then you have other resolutions inside, but a specific pod related IP address. Okay, so each pod additionally gets its own stable host name record. Okay, in this format, pod name dot training worker. So we will see all of this actually in the labs in the coming session. Okay, so I'm just trying to cover the concepts first and then do the lab, because this is a bit of a new thing in terms of people who are actually trying to utilize AI workloads, right? And this has to be made a bit clear. So that's the reason the port address, the target port, okay, and so on and so forth. Let's try to see how it works basically. So the basic idea here is there is this service training worker, this pod, and then basically there are three workers created: worker 0, worker 1, worker 2. So this is a typo. So here, so this particular thing should come here. So this arrow. So this is the backbone of distributed training. This basically means a regular IP address will resolve all the workers to one virtual IP, and then this is basically a stateful set, okay, which gives each pod the stable ordinal name this DNS scheme will relies on. So this basically, this is how we are trying to use these commands. We will see what these commands get. So we are talking of ordinal stable pod identity for distributed training. So we get three replicas get stable, ordinal index names, worker 0, worker 1, worker 2, instead of a deployment random hash suffixes, which basically is like a virtual IP, then giving certain IPs to them. So this is basically like a approach wherein we are binding, okay, the training worker headless service via service name. So each pod actually inherits a specific predictable DNS record or the IP address, right? So pod identity survives rescheduling. That means a replacement worker one keeps its name, its ordinal, and its DNS entry. So that basically means that this is a way of rescheduling. Actually it survives rescheduling. That's what it means, okay, because it basically has its own name, okay, the IP and the DNS. Okay, so this is how the state set worker is. We'll see that. And how it basically works: each pod is individually addressable. We verify the peer discovery, we see whether the lookup for this particular worker, and then there is this ordinal startup order, okay, and then there is this rank 0 coordinator, so on and so forth. But this is how it is. So that is basically related to how the IP address for the workers are created. Now, this is a load balancer service, which is basically for a tiny inference load. Okay, so we are talking of local load balancer side, right? So the basic idea here is we have a service, and this kind of a service is basically a load balancer service. We are exposing an inference endpoint outside the cluster. So there's a cluster, there is inference endpoint, and people can actually uh, visit those points, right? So load balancer requests an externally reachable IP from the cluster's cloud, the production pattern for a real inference endpoint, as opposed to cluster IP or node port. So internal cluster IP is internal, but here we are talking of real inferencing endpoint nodes, okay? And we are trying to route the external traffic on port 8080 to the tiny inference deployment port pods on container port 8000. So 8000 colon 8080 is your traffic port, right? Uh, so this is how actually it's going to happen. We'll try to understand the context first. There is this service tiny inference load balancer which is working. There's the information coming from the client which goes to the pod's tiny inference, right? So the idea here is requires the tiny inference deployment to already be running. The selector has nothing to route to otherwise. So that basically means there is one service which will be running actually. On the Docker desktop's local Kubernetes, load balancer services publish on localhost automatically. So no cloud load balance controller needed. So we are talking of local Kubernetes. We are not talking of the cloud local load balancer controller now at present, okay? But as you go along, this particular thing will emulate and give you the feel of the actual load balancing which happens in the production environment, and that is the reason why I have taken this specific example, okay? So on a real cluster, this provisions an actual external IP via the cloud provider or metal load balancer on a bare metal, right? So we are talking of real cluster provisioning. At present we are not doing that, but we are trying to do it in our own Kubernetes one node setup, okay, and various pods. So we will see how basically these provisioning happens, okay, load balancing actually happens. So this is how it is. Now one of the things which we should understand is the gateway. And gateway, basically we are talking about the inferencing gateway. So the gateway basically is gateway class basically, and it basically gives you a provision, okay, to listen to a specific port, okay, and then which links to the Docker desktop's own engine, and basically in the namespace type of stuff, right? So this is what a gateway is going to do for you. And the gateway class, basically then you have this gateway 8082 and then the proxy, okay? So the listening thing, the local port, and then you have the state of listen there, okay? So then this gateway API inference gateway class, then inference gateway, is the replacement for ingress class. Ingress, I told you, is an old thing. Now people are using gateways, so it is basically like superseding ingress. Okay, for various reasons. Okay, so this is a cluster controller. You can create it once for the platform and so on and so forth. We'll see it in the lab when we do it. So this is how it works. So there is this gateway class, and then you have this gateway for team alpha, gateway for team beta, and then there are certain feature teams, if any. So there are gateways for all these teams. So every gateway in the cluster references a gateway class by name. To pick its implementation, we have to have this controller of Istio actually registered before relying on this. Okay, kube control, get gateway class, so on and so forth. So we'll see all of those. And then the namespace, we understand. So there's this LLM inference route that basically means you are having to define a path based routing rule, okay, and attaches that to the gateway through the parent references, so on and so forth, right? And then you create an ML team inside the own namespace, right? And then this is like not like a classic ingress. So no cluster admin access is needed when you create a specific team inside a specific namespace, right? Like team alpha, team beta, or whatever teams. So this is how actually the gateway, the HTTP route, and LLM service works. Okay, so you have this traffic splitting canary rules, which we will try to use and build on the top of this same HTTP route resource. So this basically means we are trying to discuss how the load balancer actually shifts the load, and then it basically can be visualized, okay, using the browser and so on and so forth. So this, I suppose, is the end of today's session. uh, Tomorrow we will start with another session, and we will try to do hands-on of whatever we have done today. So you can just have a revise of whatever is this, and then we will see the tomorrow hands-on. Thank you.